Good day. This is Peter of Ireland, grade 11 UMS, Mount Victoria. For our topic for today is all about exponential growth and decay. And I have two problem and each one exponential problem have problem of each exponential growth and decay. So let's start. The first one is exponential decay. Exponential decay. A bottle of is put into a refrigerator. The temperature inside the refrigerator remains constant at 3 degrees Celsius, and T minutes after the bottle is placed in the refrigerator, the temperature of water in the bottle is 0 degrees Celsius. I theta degrees Celsius. D theta divide over d time equals 3 minus 0 over 125. Theta equals a e power to the minus 0 not by not point not 8 time plus 3, where a is constant. Given that the temperature of the water in the bottle when it was put in the refrigerator was 16 degrees Celsius, find time taken for the temperature of the water in the bottle to fall to degrees Celsius degrees 10 degrees Celsius, giving your answer to the nearest minute. So let's start. So all you have to do is wait. All you have to do is wait sir, wait. I'll just write it first because naglisod ko po sa cellphone. Wait sir. So I'm done answering sir. So there is my answer, 77 years to the minutes. The first is theta equals the constant a multiplied e to the power minus not point not 8 time, and then plus 3, and what we given is that initially when t north note that the temperature of the bottle was 16 degrees Celsius. So we can say that t equals 0 and the temperature given by the theta equals 16. And if we substitute these two equation, here we got 16, 16, 16, the constant a multiplied to the power of 0. 0 is no longer 0, it's gonna be 1, and then plus 3. So a equals 13, and both side 3 to the both side is 13, so a equals 13. Theta equals 13 e to the power of minus 0 not point not 8 time plus 3. So let's move on to this one. Starting at here, when equal 0 is going to decay like this, is going to approach 3 as t gets bigger. Let's mark that line and we call as asymptote asymptote asymptote. So then 10 is over to the down, and let's find the t, the big t. Wait, big t. When theta equals 10, t equals big T. 10 equals 13 e to the power minus naught by naught 8 t equals 7 over 13. And if I have to take the natural logs to the both side, I'm going to have, well, put this side first. I'm going to have 0 not 8 time equals natural logs of 7 over 13. T equals minus 1 over naught by point naught 8 natural log 7 over 13. And the answer is, and to get t, all I've got to do, divide both sides to 0 naught by 0.008. So the answer is 77.37. And to the nearest minutes, let's go to the round off of 77.4 and not this round. So the answer is 77 to the nearest minutes. And that's all for today to the exponential decay. Good day. This is Peter of Ireland, grade 11 UMS, Mount Victoria. Our topic for today is all about exponential growth because I'm done of exponential decay. So let's go on. The problem is a population is growing exponentially. We also know there was bacteria, 200 bacteria in 3 days ago and 1000 bacteria in 1 day yesterday. How many bacteria will be there by tomorrow? What? So let's solve it. So wait, sir. I'm gonna write the solution here. I'll be right back. So this is my solution about the problem of exponential growth. So let's start. The first is, wait. So again, we know what do we know? We know the population P of t can be described by a times e to the k t. Again, we can say this because the population grows at a rate proportional to the population, okay? So I guess we have some information. We don't really know a lot of things. We don't know the initial amount. We don't really know the key, the growth rate. But what do we know is we know that 3 days before now. So I'm going to let t equal negative 3 days prior to now. Okay? Well, let's see. Okay, we still don't know t. We can plug in the negative 3. We know that the population 3 days ago was equal to 200. Likewise, we know the population 1 day before. So again, that's going to be a times e to the k times negative, and we know that equals 1000. We want to know the value of the population on 1 day later. Okay, so I'm going to do is I'm going to take our two equation here. This one, I'm box. We'll use this solve for the everything that we need to solve. So we've got a times to the, I guess, negative 3 key, that's going to equal 200 at times e to the negative 1 key. We know that the equals is 1000. So what I'm going to do is I'm just going to divide these two equations so that if I to the negative 3 key equals 200, well, if we divide the times to the 3 e to the negative k, well, since the numerator is equal to 200 and the denominator would be equal to 1000, we can just set up this nice little equation. And the point of doing this is, we'll notice the a's you're going to cancel out, so we'll be left with the negative 3k over e to the negative k. Well, we can always rewrite that as 1 over if we put the negative 3k in the denominator, if we'll come e to the positive 3k, so that will give us that take lets us to do, wait, to reduce that, I'm just half 1 over 5th, and we could multiply e to the 2k and then multiply the 5 over. To solve this, we can take the natural logarithm of both sides. And well, let's see the natural logarithm of e to the 2k. That's just going to leave us with 2k. So it says the natural logarithm of 5 over 2, that's going to equal k, our growth rate. Right. So let's see again. We know that the population at the time that at times it to the key, but again we've got key now the natural logarithm with as a 5 over 2 times t. I'm going to simplify this a little bit with just this one, sorry. This a little bit, we could rewrite this as e to the natural logarithm of 5 times half, right? That's going to give us our multiply the exponents. Natural logarithm of 5 and half e to the natural logarithm of 5, that just 5 we still have to the half power times t. So really we could even simplify this again. We would really have 5 to the 1 half, that the square root of 5 times. So that's more simplified equation to describe the population. And then, alright, we'll have I'm going to do now is we need to figure out initial value. So I can use either one of the I can use the either one of these original equation. This equation. Either one of these equation, and we set the population at the time. I guess let's use negative 1. We said okay, so we can describe that by times the square root of 5 times t, reduce that, but again the population 1 day prior, that was equal to 1000. I should be careful I didn't replace my t there. So heard to the population when something wrong, kalimutan ko ta. T equals negative 1, so that looks a little bit better, this one, I guess. Equation will this is just over the square root of 5, that equals 1000. Well, if we multiply both sides, we'll just get initial amount is the square root of 5 times 1000. So population time equals square root of 5 plus 1000 times square root of 5 time, and that's our constant a. So population time is 1 equals square root of 5 times 100 times square root of 5. So let's just put in this one equals and 1 equals 5 times 1000 equals 5000. That's the answer of the bacteria. The bacteria tomorrow. Bacteria be the day tomorrow. And that's all set. Thank you and God bless.